illustrate the concept of sound frequencies is listening to loud music played in the home next door. The bass, or low frequency, is often heard through the wall. Higher frequencies are often attenuated or absorbed by the walls of the home. One cycle of a sound wave is composed of a complete positive and negative pressure change. The distance traveled during one cycle is called the wavelength. The frequency of the wave is measured in cycles per second, or hertz. Audible ranges of wavelengths heard by humans are between 16 and 20,000 hertz. Ranges higher than 20 kilohertz are not heard by humans and are considered ultrasound. In the case of typical ultrasound imaging, the frequency range is between 1 and 20 megahertz. Smaller piezoelectric elements vibrating relatively faster generates higher frequencies. Larger piezoelectric elements vibrating relatively slower will create lower frequencies. Several parameters affect the clarity of an ultrasound image. One of them is frequency. Lower frequencies are less attenuated and provide better penetration, which is good for deeper structures. Higher frequencies provide better resolution for shallow structures. For optimal imaging, it's critical to select the transducer with the right frequency for the anatomy being examined.
the heart of most ultrasound systems is a device called a transducer, which uses an array of piezoelectric crystals. A piezoelectric crystal vibrates when an electric signal is applied, producing high-frequency sound pressure waves, which we call ultrasound. More importantly, this type of crystal can also work in reverse. It can produce electrical signals when it detects high-frequency sound pressure waves. When a transducer directs ultrasound waves into the body, they pass right through the skin and into the internal anatomy. As the waves encounter tissues with different characteristics and densities, they produce echoes that reflect back to the piezoelectric crystal. This happens more than 1,000 times a second. Returning echoes are converted to electric signals, which a computer converts into points of brightness on the image, corresponding to the anatomic position and the strength of the reflecting echoes. A medical transducer contains a large array of crystals, which allow it to make a series of image lines that, together, form a complete image frame, called a sonogram. In addition, all the crystals are repeatedly activated many times in such a way that a complete image frame is formed around 20 times per second, so that real-time motion is displayed in the ultrasound image.
Smaller piezoelectric elements vibrating relatively faster generates higher frequencies. Larger piezoelectric elements vibrating relatively slower will create lower frequencies. Several parameters affect the clarity of an ultrasound image. One of them is frequency. Lower frequencies are less attenuated and provide better penetration, which is good for deeper structures. Higher frequencies provide better resolution for shallow structures. For optimal imaging, it's critical to select the transducer with the right frequency for the anatomy being examined.
Has over 9,000 elements. The exact number is 9,212. I often get asked why we need so many. We need all of these elements for the three-dimensional acoustic beam forming that allows the X61 to steer and focus throughout the entire field of view. Let's first look at why. A conventional one-dimensional transducer has a fixed aperture and a fixed lens. We want to image in a single plane, but the aperture and lens provide an elevation beam pattern like this. we get good elevation focus or slice thickness over a limited range, with increased clutter and haze in the near field and far field. A 1D array can steer and focus within its single imaging plane, but it can't scan a three-dimensional field of view. It can't steer in the elevation direction. Some so-called matrix transducers provide a few rows of elements in elevation, which provides multiple elevation focal zones and better depth of field. This provides some improvement in slice thickness and focal range, but the improvement is limited by the small number of rows. Also, this type of transducer can't steer in elevation, so it's still imaging only a single plane. In an X-matrix array, the elevation dimension is separated into elements in the same way that it is in azimuth with many rows. Having many rows with independent delay control provides the same degree of electronic control of the acoustic beam in elevation as there is in azimuth. We can focus the beam over a much larger focal length, resulting in good slice thickness everywhere. We can also use this electronic control of elevation to steer the acoustic beam throughout the entire three-dimensional field of view. This provides novel modes such as X-plane with two planes displayed simultaneously in real time, as well as 3D.
بسم الله الرحمن الرحيم. سنتحدث اليوم عن مشاكل التصوير الثلاثي الأبعاد. بداية عند التصوير بطريقة منتظمة، عندما تكون يدنا بسرعة منتظمة سيكون الوضع على الشكل التالي. إذن شكل واضح للمكان المصور. ماذا لو كانت سرعة اليد أعلى من المطلوب؟ نلاحظ تضيق أو أن الصورة مضغوطة. ماذا لو كان السرعة أقل من المطلوب؟ نلاحظ أن الصورة تمددت على الشكل الحقيقي. ماذا لو تنفس المريض خلال عملية التصوير؟ هذه هي أهم المشاكل التي نتعرض لها عند التصوير ببروب الثلاثي الأبعاد. وشكرا لكم.
has a number of elements aligned in a row, and these elements are excited in groups and echoes detected one at a time to form the lines of an image, perhaps 100 or 200 lines that make up a B-mode image. And the plane of this image is defined by the direction that the transducer is pointing in, and if we want to change that plane, we have to move the transducer either with our hand or with a motor in some transducer probes. The X61 is quite different. It doesn't have a line of elements, it has a two-dimensional array of elements. And although the area of the footprint of the transducer is comparable to that of a conventional abdominal transducer, there are a great deal more elements there, not 100 or 200, but 9,000 elements in the case of the X61. And I think you can see immediately that such a transducer, if one had control of all of those elements, could be used in many different modes. One of them is in a conventional beam mode, but also, of course, because you can steer the beam in the elevation direction, that beam mode can be translated without moving the transducer, and indeed you can make two or many more simultaneous real-time beam mode images of adjacent slices. The transducer can also image in the orthogonal direction, and once again it can do that simultaneously with imaging in the long axis direction. And this simultaneous orthogonal imaging, where two B-mode planes at right angles to each other are presented together in real time, is one of the fundamental modes of imaging that the IU-22 provides with the X61 for abdomen and OBGYN applications, and it's called X-plane imaging. Finally, the transducer can be made to sample the entire volume that's available to it, and it's quite a big volume because it's a wide transducer. It can scan up to more than 100 degrees, and these volumes of data can be acquired and processed in real time. Transducer that constitutes this advance, because even if you've got 9,000 element transducer, how are you going to connect it to an ultrasound machine? You can't make a cable with 9,000 wires inside it. And really the enabling technology that has allowed this development to take place is that of the beamformer, the 9,000 channel beamformer, which is not in the ultrasound system but in the probe itself. So those 9,000 elements are connected to integrated circuits which then form the beam and send through a similar wire to the ultrasound system sets of data which correspond to the commands given to it by the host system. So when you scan with an X61, you're literally holding a 9,000 channel modes and begin with an ordinary B mode scan. And if we were to use a conventional transducer, we're always faced with the fixed elevation focus. The slice thickness is at a minimum level at the elevation focus, then gets fatter towards the transducer and continues to get fatter beyond the focus of the elevation. This is fixed by the lens of the transducer. But with the X matrix, the thickness of the plane is determined and controlled by the beamformer itself. And so extremely uniform images can be made which show contrast resolution to those with which we're familiar with a 1D transducer. But if we look at this gallbladder, for example, with the X61, we can also go immediately into a real-time mode, the X-plane mode, and see two orthogonal views of the organ simultaneously. Here a long axis and a short axis, and here, just by moving the transducer, two orthogonal long axes. So that's X-plane imaging. And we can also use the transducer to acquire all of the data. And again, this can be done live or in a snapshot. And this enables us not just to produce two orthogonal planes, but to produce, to reconstruct, in fact, a plane that we never see with conventional ultrasound imaging, the C-plane, the plane that's at constant depth from the transducer, the one that's orthogonal to the two right-angle B-mode planes we can obtain by rotating a conventional transducer, or live using the X61 in X-plane mode. And here you can see the two X-planes with the C-plane below it. And of course, if we take those three orthogonal planes, all kinds of processing are available to us. QLab does this on board the system, and this particular depiction of the biliary tree is made by inverting the echo-free areas and then rendering them, so we get a kind of a virtual view of the three-dimensional branching structure of the biliary tree. There are many other things that can be done with the X61. One of them is to, instead of making a very uniform thin slice, to make a uniform but slightly thicker slice. And this so-called elevation compounding or thick slice imaging reduces speckle and increases contrast resolution, allowing you to see with better clarity structures of near equal echogenicity. So thick slice imaging is available to enhance contrast resolution. Very thin slice imaging gives the highest spatial resolution, and the ability to vary these is uniquely associated with a matrix array. So in summary then, I've just gone over some of the basic properties of these arrays. It's a new level of precision basically in the positioning of ultrasound beams in tissue. And these are done with the IU-22 to provide thin slice beam mode images, simultaneous orthogonal plane or X-plane imaging, which of course is a live mode, multiple plane imaging as well, including C-mode images, which can also be made live, 3D visualization, and this includes both the ability to show surfaces, as I gave an example of, but also MIP imaging, that's maximum intensity projection imaging, where we visualize an entire structure and see through it, and this may have some applications in the abdomen and gynae areas. We can do elevation compounding, which reduces speckle and improves contrast resolution, and Doppler and contrast modes are already available on this. And I think, above all, this new technology gives us a glimpse into what the future of ultrasound is going to be like, where
To clean a transducer used externally on intact skin, begin by disconnecting the transducer from the ultrasound system. Dampen a clean gauze pad with water and wipe the transducer, cable, and connector to remove gel or particles. Use a compatible disinfectant wipe to complete cleaning. To perform a high-level disinfection of the transducer, take care to keep the cable strain relief and connector of the transducer dry while immersing the transducer in an approved disinfectant. You can submerge the transducer up to the level indicated on the diagram. To ensure your transducers are submergible, look for the IPX8 designation on the label located on the transducer connector. Do not submerge a transducer without this designation. Caution: leaving the transducer in the solution longer than suggested by the manufacturer may result in damage. After cleaning or disinfecting, use a clean cloth to dry the transducer and store appropriately. Do not use a spray-type disinfectant, as the pressure may force the cleaner under the lens and into the transducer casing.
Doppler ultrasound is used to detect flow within vessels. To demonstrate the use of Doppler ultrasound, we will obtain a mid-long axis view of the common carotid artery using a high-frequency linear transducer. Activate color Doppler on the device and position the color box over the lumen of the common carotid artery, or CCA. The color bar serves as a legend that maps color to the velocity and direction of blood flow. Here, the red color indicates flow toward the transducer, and the blue color indicates flow away from the transducer. The intensity or brightness of a color is a representation of the velocity of flow. By convention, the display should be configured so that flow within arteries is represented as red and flow within veins is blue. The color bar can be inverted. This is generally done to display normal directional flow in an artery to be represented with red color. Adjust the color gain if necessary, so that color only appears in the lumen of the vessels, not outside of them. The normal CCA has a laminar flow pattern. This means that flow velocity in the center of the vessel is higher than near the wall of the vessel. Activate the spectral Doppler display mode. The spectral Doppler waveform enables the user to graphically visualize the velocity of blood flow over time. The system is dependent upon the user to set a number of parameters so that the correct result is displayed. First, the Doppler sample volume gate should be positioned in the center of the lumen or in the area of highest velocity. Next, adjust the sample volume. The sample volume is the area of flow that will be represented in the waveform. The sample volume size should be set to approximately 1/3 of the vessel diameter. Another user configurable parameter is the angle correct setting, or AC. The AC corresponds with this bar. The purpose of this setting is to provide a correction factor in order to achieve the correct inclination angle. The goal is to align the AC bar with the direction of flow. The AC value should be in the range of 0 to 60 degrees for the carotid artery Doppler study. Obtain a numeric value for flow velocity by using the measurement tools. Freeze the image and place a measurement caliper at the point of peak systolic velocity in the waveform. The end diastolic velocity can be measured by placing the caliper at the lowest point of the trough just before the systolic waveform.
Logic E9 elastography. The Logic E9 elastogram is achieved by positioning the ROI box around the region of interest and then applying a slight compression at the skin surface with the ML 6 to 15 transducer. The soft lesion deforms under the pressure. The chromatic scale assigns soft tissue as red and hard tissue as blue. The elastogram indicates that this lesion is soft. The hard lesion does not deform under the pressure like the soft lesion. This elastogram indicates that the lesion is hard. The quality indicator provides visual feedback to monitor compression technique. The indicator will appear green when a proper technique is used, and blue, yellow, or red when the technique needs to be modified. There are many display formats available with Logic E9 elastography. Full screen display mode, side-by-side, side-by-side with imported digital mammogram, or fused with the patient's previously acquired PET, MRI, or CT using volume navigation.
has a number of elements aligned in a row, and these elements are excited in groups and echoes detected one at a time to form the lines of an image, perhaps 100 or 200 lines that make up a B-mode image. And the plane of this image is defined by the direction that the transducer is pointing in, and if we want to change that plane, we have to move the transducer either with our hand or with a motor in some transducer probes. The X61 is quite different. It doesn't have a line of elements, it has a two-dimensional array of elements. And although the area of the footprint of the transducer is comparable to that of a conventional abdominal transducer, there are a great deal more elements there, not 100 or 200, but 9,000 elements in the case of the X61. And I think you can see immediately that such a transducer, if one had control of all of those elements, could be used in many different modes. One of them is in a conventional beam mode, but also, of course, because you can steer the beam in the elevation direction, that beam mode can be translated without moving the transducer, and indeed you can make two or many more simultaneous real-time beam mode images of adjacent slices. The transducer can also image in the orthogonal direction, and once again it can do that simultaneously with imaging in the long axis direction. And this simultaneous orthogonal imaging, where two B-mode planes at right angles to each other are presented together in real time, is one of the fundamental modes of imaging that the IU-22 provides with the X61 for abdomen and OBGYN applications, and it's called X-plane imaging. Finally, the transducer can be made to sample the entire volume that's available to it, and it's quite a big volume because it's a wide transducer. It can scan up to more than 100 degrees, and these volumes of data can be acquired and processed in real time.
Be sure that your TGC does not give you an image where you have an area that is too bright, either in the near field, the midfield, or the far field. Be sure to adjust the TGC so that you have uniformity of the echoes. Let's look at this image. Notice this manufacturer shows us where our TGC slope is. These echoes are all uniformly the same brightness. This TGC was set properly.